In this group of tests, what we will do now is to try to show that the expiration date or the time to the event or the probability of survival is larger than something. So we want to do a test with only one sample, and we want to say something about mu. So that is the location of the survival parameter, or the reliability, that is the complement of this of the survival rate. It is the same as survival rate. And the word reliability is coming from engineering, where they want to do some quality control on the products that they produce. Okay, so let's say that we want to show that the drug in a syrup lasts for at least 2 years. How many bottles of this syrup do we need to test to show that the mean expiration time is larger than 2 years with a confidence of 95%, if we are going to test the bottles only for 2 months? So we don't want to wait for 2 years. We want to wait for 2 months and then project whatever we have seen into the future. And we can do that assuming what is the distribution of the probability of having the event. Our event now is spoiling, and we accept 0 spoiled bottles. So we will track a number of bottles for 2 months, and then if 0 of them expire during these 2 months, we can guarantee that the expiration rate or the expiration time of the rest of the bottles is at least 2 years. Okay, so let's see how we can do that. So let us call mu the mean expiration rate date, and the mean expiration date we want to show that it is larger than 2 years, and the null hypothesis is that it is smaller or equal. So there are two ways of making these experiments. So the first one is testing n bottles that we have to calculate, and we fix the time. So we fix the time and we calculate how many bottles do we need to track during this fixed time, or we fix n and then we calculate for how long we have to track those bottles. Okay, so in this experiment we have fixed the time, so let us calculate n. So this is the shape of our hypothesis test, and then we want to construct a confidence interval on mu that is of this form, and it has probability 1 minus alpha. So if the null hypothesis is true, the null hypothesis is rejected if this sum is smaller than alpha, and this sum is from 0 to the number of the maximum allowed number of failing individuals. This is a parameter you choose when you design your experiment, and this b is the binomial probability with n and tf parameters. So this is the number of spoiled bottles that you have observed, r, and then the parameters are n, the number of bottles, and tf somehow it is not the probability parameter, but it fixes the survival at tf. Tf is the observation time, so the 2 months in our example. And yeah, in this survival we are assuming that the mean survival time is this one, mu 0. Okay, so in this equation here, if we fix n, so we have three parameters. We have R, we have capital R, we have capital N, and TF. And we want this sum to be smaller than alpha. So if you fix 2, then the third one can be calculated. So that is why we have fixed R to 0. So we don't want to see any spoiled parameter, any small spoiled bottle. And then we have fixed TF, the 2 months of observation, and then we will calculate N. So depending on what is the distribution of the survival times, so if we assume it is exponential, Weibull, or normal, then there is a relationship between TF and the survival time and TF, and these are the relationships that are coming from the previous video in which we were analyzing these three distributions. So given TF or given the survival, we can compute TF or vice versa. Okay, so now we have everything to compute our sample size. So in our case, we have fixed R equals 0. So during this period, we don't want to see any spoiled bottle. If we see, we will reject the null hypothesis. The null hypothesis is that, or we cannot reject the null hypothesis. The alternative is that it is larger than 2. So if we see any spoiled bottle, then we cannot reject the null hypothesis. Okay, so TF is 2 months. 2 months is expressed in years. It is this one. Mu0 is 2 years, and then we calculate the survival at TF. So the survival at TF is 0.92. So only 8% of the syrups they spoil within 2 months. And we use the rejection equation with R equals 0. So the rejection equation is this one. So we compute this one is smaller than alpha. So well, we put it equal alpha, which is simpler. So this is with R equals 0, and then it is simply a matter of solving for N. So N has to be larger than 36. So we need to track 36 bottles of this syrup for 2 months, and if we don't see any spoiled one, then we reject the null hypothesis. This is the opposite case in which we fix N and then we calculate TF. So we want to show the same thing, but now we will study 100 bottles of this syrup, and the mean expiration rate time we want it to be, we want to show that it is larger than 2 years, and we accept 0 or 1 spoiled bottles. So we will assume that we have a Weibull reliability with beta equal 2. So beta equal 2, let us go back to this one. So beta equal 2 is this one. So it is one in which the hazard rate increases with time. The one that we had before, it was the exponential, that is this one in which the hazard rate is constant. So this one probably it is more representative of many products like syrup. Syrup probably as time passes, it is more and more likely that it spoils. Okay, so let us go back to our problem. Okay, so we have 100 bottles. We think that the spoiler rate grows with time, and then we need to solve the equation, the previous equation, for TF. So first we have to solve it for the survival at TF, and then we will solve TF from there. So this was the rejection equation. This is the rejection equation, and we have said that we admit 0 or 1 spoiled bottles, so we will have this one with r equals 0, this one with r equal 1, and then this has to be smaller than 0.05, and we solve for STF here. So STF, so the survival at TF has to be 0.95, and now we look for the time at which the survival is 0.95, and for the Weibull with parameter beta equal 2, we go to here. So given STF and beta, we can compute TF. Okay, so it is this one, 0.4 years, that is 160 days. So we have to track these 100 bottles for 160 days, that is 5 months, and then a little bit more than 5 months, and then if 0 or 1 spoil, then we cannot reject the hypothesis that, where is it? We cannot reject the, so if we see 0 or 1, we reject the null hypothesis, and then we can claim that the mean survival time is larger than 2. Okay, so that is for mu. So we have made tests thinking about mu, but we can also make tests thinking about the survival time. So the survival time, we may want that to show that the survival after 5 years, for instance, is larger than 95%. Okay, so for instance, let's say that we are implanting cochlear devices. We want to guarantee that 95% of the devices work after 5 years of function, but we don't want to wait for 5 years. So how many implants do we need to observe during 2 years with no failure? And we will assume now a normal reliability with a standard deviation of 2 years. Okay, so again, we can have 2 ways of making this test. So either we fix the time of observation and then we have to calculate n, or the opposite, we fix the number of units that we will track, and then we will track them for a time that we have to calculate. Okay, so this is our hypothesis test. So we want to show that the survival rate after a time t0 is larger than a something, and the null hypothesis is the opposite. But we will track the units not till t0 but till tf. Okay, so we want to construct a confidence interval of this form, and the null hypothesis is true, is rejected if this sum, that is the same one that we had before, is smaller than alpha. And again, we have 3 parameters: r, that is the number of spoils that we admit, n, the number of devices that we are tracking, and tf, the length of our experiment. And again, we have these relationships between tf and the survival times. So here we are relating survival time at tf with survival time at t0. So these equations are different from these ones. Here we were relating the times to the location parameter, but here we are relating the time to a comparison between survival rates at 2 different times. So they are coming from the same distribution, but it depends on what is your comparison, what are the parameters that you are using to compare. Okay, so we are assuming normal reliability, so we will be using these ones. Okay, so in our case, we will track the devices for 2 years, but we want to infer something about 5 years, and the sigma is 2 years. So the survival time that we want to show after 5 years is 95%. So with this we compute C0. So C0 is the time at which, or the critical value of the normal distribution, at which 95% or 1 minus 0.95% of the distribution is there. So it is minus 1.64. And then CF. Okay, so CF is, let us look at here. So it is C0 plus TF minus T0 divided by sigma. So we have everything. So it is C0 plus 2 minus 5, 2 because it is TF minus T0. So we will observe the devices for 2 years, but we want to infer something at 5 years divided by sigma. That is the standard deviation of the survival time. So this is minus 3, and then we calculate the survival at TF. So the survival at TF is 0.999, and then we can substitute into the rejection equation with R equals 0. So the rejection equation is this one, and we substitute all the values that we have, and it is 0.999 to the n power has to be smaller or equal 0.05. So n has to be larger than 3,000, almost 4,000. And this may look like a very large number, but we have to take into account that we want the device. So most devices will be still working after 5 years. We will observe only for 2 years, so even more devices will be working. Very few will fail, and that is why. So you see the survival time after 2 years is 0.999. So only 8 out of 10,000 will be broken. So that requires a lot of devices to be tracked, because otherwise we cannot see any of these breaks. Actually, we want no break in 4,000. Okay, so this is the alternative design in which we fix the time, we fix n, and then we have to calculate the time for which we have to track them. Okay, so the problem is the same. We want to show that the first 1% of the implants, so some of the implants will fail. We want to show that 1% of these, after a given time, all of them will have failed. So you want to see what is the time at which 1% of these have failed, and you want to show that this is larger than 4. You will track 100 cochlear implants, and for how long do you need to track them? Okay, so this is the scheme of our hypothesis test. So we want to show that the time to reach a given percentage is larger than something, and the null is the opposite. And we can use the same equations as we had for in the case above. So let's say that we have R equals 0, so we don't accept any broken device. N is equal 100, so we can compute the STF from the rejection equation. So STF has to be 0.97, and now we have to calculate the CF at which this happens. So STF is 0.97, and this has to be 1 minus the cumulative distribution of the Gaussian. So the cumulative is 0.0295. So now we have to to look for the CF in the normal 0, 1 Gaussian, such that this area is to the left, and this value is minus 1.8. And then we also need the C0. So C0 is so we want to show we want to calculate something on the time at which 1% of the devices have failed. So this 1% is a survival of 0.99, and again we need to calculate Z such that from that point to the left we have 1%, so it is minus 2.3, and then we can calculate TF. So we know what is CF, what is C0. We know the relationship between CF, C0, TF, and T0, and then we can solve for TF. So TF is 4.88 years. So we have to track them for almost 5 years, and we cannot see any single break. And then if we don't see any break, then we would reject the null hypothesis, and we would accept that the survival time of, so not the survival time, the time at which 1% of the implants fail is larger than 4. So with this we finish this group, and then in the next group we will study survival rates, survival curves of 2 samples. We will compare the survival in 2 different conditions. This would be all.